Hi everyone. So we're going to review for test 4. So I'm just going to go through the practice test, or as much of it as I can. I'm going to start with number 1, right? So we're converting from exponents to radicals. And the key to this is, right, when you have a fraction as an exponent, right, knowing whether the numerator or the denominator is the power and which is the index, right, or the root. And I think I mentioned this in a previous video that the way to think of it is, right, when you have something like, let's say, x to the 2, right, that's just x squared, right? There's no radical here. It's just x to the 2 over 1. On the other hand, if you have something like, let's say, x to the 1/3, right? So this is not the same as x to the 3, because 1/3 is not the same as 3. So what is it? It has to be the cube root, right? It has to be the cube root of x. So it's going to be the denominator that tells us the index, right? If you have x to the 1/2, that would be the square root of x. Just keep in mind that we usually don't put the 2 there, right? Because we use the square root the most often. The 2 is just, you can just leave it off. And it's just assumed to be a 2, right? In much the same way that when we write x, we're not writing x to the power 1. We're just assuming it's a 1, right? So in the same way here, when you don't see an index, we're assuming that, right, it's a 2 and not a 1, because the first root of x would also just be x, right? So in that case, there's no reason to write a radical at all. All right, so with that, I think we can do part A pretty quickly here. We have v to the power 5 over 2. So the denominator is 2, so this is the square root of v to the 5. Again, the 2 is optional, so it's really just the square root of v to the 5. Right. You could, of course, also write the 5 on the outside. This is the square root of v, all raised to the 5th power. So it turns out that these are the same, at least when v is positive. And we're assuming that v is positive here. Right. So for part B, we have x minus 1 to the 3 over 4. So this has to be the 4th root of x minus 1 to the 3, or the 4th root of x minus 1 to the 3. Right. Again, it works either way here. We're assuming that x minus 1 is positive. Right. So part C, y to the 2/3. Of course, that's just the cube root of y squared. Right. So again, just be careful you don't write the square root of y cubed, right? Because that would be y to the 3 over 2, not 2 over 3. So yeah, don't get those mixed up. And again, the easiest way is just remember these two cases. The numerator has to be the power. The denominator, right, has to be the root or the index. All right, so part D, z to the 1/5 is just the 5th root of z. Right. Okay, so that's number 1. Just doing it very quickly. Right, and then for number 2, we're going the other way. We want to convert from radical form to exponents. And so for part A, this will be number 2, we have the 8th root of a to the 3. So remember, the power has to be the numerator, so this is going to be a to the power 3 over 8. Right. Not 8 over 3. That would be the cube root of a to the 8. Right, right, so part B, we have the 6th root of b to the 4. This would be equal to b to the power 4 over 6. right? Now, you might say, well, isn't 4 over 6 2 over 3? Fair enough. But this is something we're not trying to simplify this. We're just converting. On the other hand, maybe it's best to simplify, just get into the habit of it. But for this question here, I would obviously accept either. It's just that you should know how to convert 4 over 6 to 2 over 3. Yeah, and just checking the answer key, I did simplify it. I did write it as b to the 2/3 instead of 4 over 6. So yeah, always reduce your fractions to lowest terms. Always simplify your answers. And then part C is the tricky one. It's the square root of x squared plus y squared. Okay. So here the index, because we're not writing it, it's assumed to be a 2. Right? So this will be to the power 1/2. And what are we raising to the 1/2? Everything under the square root. And that's it. Right? Don't make the mistake of thinking that, oh, I can distribute the 1/2. Right? This is x to the 1/2, x squared to the 1/2 plus y squared to the 1/2. Oh, and then I know the rule of exponents that say I can just multiply 2 times 1/2, which is 2 over 2, which is 1. And then this would be x plus y. But that's not what this is, right? So you have to be very careful here that you don't make the mistake of saying that this is x plus y, because it's not. And if you just try some numbers, like x equals 1, y equals 2, or just really simple numbers here, you'll see that it doesn't work in most cases. So yes, so do not make that mistake, right? This, you have to leave it like this, and that's the best you can do, right? And that's because we're adding, just to remind you, if you had the square root of x squared times y squared, that you could split up, and you could write this as x times y, assuming that x and y are positive. Otherwise, you need absolute value, right? So yeah, there might be a question on that coming up very shortly. All right, let's go on to number 3. Okay, so here we just want to simplify. Part A is the cube root of y cubed, right? So if you're not certain what this is, you could convert it to an exponent. It would just be y to the 3 over 3, right? Because the exponent and the index happen to be the same. And 3 divided by 3 is just 1. So this is just y to the 1, or just y. Okay? So even though they're not asking us to convert from radicals to exponents, in this case it might be helpful. And the same thing is true here, right? Right, we could think of this as x to the 8, y to the 12, and then not raised to the power 4, but 1 over 4. And then just use the rules of exponents, right? This is just x to the power 8 over 4 times y to the power 12 over 4, which is x squared times y cubed. So that's one way to go about getting to the final answer. The other way, of course, is just to split them up as the 4th root of x to the 8 and the 4th root of y to the 12, and then realizing that this is just the 4th root of x squared to the 4th and the 4th root of y cubed to the 4th. And just like here, you can think of the 3's as kind of canceling, right? 3 divided by 3. Here, we're thinking of the 4's as canceling, right? When the index and the exponent match, they tend to just cancel each other out, right? And so that's where we just get x squared y cubed. So that's another way to think of it. That's probably how we did it originally. Part C, as always, is the tricky one, right? Because this is c minus 5, and if you're using exponents, it would be 2 over 2. Remember, there's an invisible 2 here, so the denominator is 2. So you might think this is just c minus 5. And, well, that's not quite right, because we're not stipulating that c minus 5 is positive here, right? So in general, if you take the square root of something squared, this is just the absolute value of a. So we're missing the absolute value here, right? So yeah, we're not assuming that c minus 5 is positive. It doesn't say that in the directions. So yeah, so you have to be careful when converting to exponents like this. Don't forget the absolute value when the index or the root is even. Right? So be careful. If it was the cube root, right, as we did earlier, there's no absolute value here. Right? But if it's the fourth root, don't forget we still need the absolute value again. Right? So it depends on the evenness or the oddness of the roots here. Okay, number 4. Okay, so number 4, 2 ships leave the same port at the same time. One travels north at 12 miles per hour. The other travels west at 5 miles per hour. After 4 miles, how far apart are the 2 ships? So what's the distance between the 2 ships 4 hours later? Okay, so this is not an easy one, right? This is one that might not have even come up in the word problems. So let's think about this, right? We have 2 ships. Let's draw a picture here, right? So this will be going up. This will be north, like on a compass, right? And then this will be east. This will be south. And then this way will be west. Right. We have 2 ships start at the same time. Let's say they start right here in the middle at the origin. And one of them travels north this way, right? And that's 12 miles per hour. And the other travels west this way, a bit slower at 5 miles per hour. Okay. So after 4 hours, right? That's how long we're waiting. How far apart are they? Right. So what do we need to know here? We need to know, we know how fast they're going, right? One's going 12 miles per hour, right? But how far does it travel in 4 hours? All right, so for that, we have to go way back. One of the first things we did were word problems or applications involving systems of equations, and one of the applications required that speed times time equals distance. So that's the relationship between speed, time, and distance. Right. After all, your speed is just how far you travel, your distance, divided by how long you took, the time. Okay, so we're looking for distance here, right? How far apart are they? What's the distance they traveled? And we know their speed. So let's take the one going north, the northbound ship. It's 12 miles per hour. That's the speed. That's how fast it's going. And we're going to multiply by 4 hours. Right? So the hours cancels, and the distance it travels is, well, 12 times 4, 48 miles. Now let's look at the one going west. And that's only going 5, it's supposed to be a 5 miles per hour. Still traveling for 4 hours, so 5 times 4, is 20 miles. Okay, so now, how far apart are they? Okay, so this one's, again, this is why this is a tricky problem. And I think I didn't, well, okay, so here's another way to think. If you look at the picture on the right here, after 1 hour, the ship going north traveled 12 miles. After 2 hours, well, 12 times 2, that would be 24 miles. After 3 hours, 36 miles. And right up here, after 4 hours, 48 miles. Okay, so this is where the northbound ship is. Okay, what about the westbound ship? So after 1 hour, it traveled 5 miles. 2 hours, 10 miles. 3 hours, 15 miles. And then 4 hours, 20 miles. Okay, so this is where the westbound ship is. And what we want to ask is, what's the distance between these two ships? So I'll call that D for distance. Okay, so think about that for a second, and hopefully you can come up with the answer. So, yep, you notice I drew a little triangle here, and that's what I was hoping you would think of, right? So just to remove the clutter here, here's that triangle again. And you can see that north and west are perpendicular directions, so this is a right triangle. This side is 20 miles, this side is 48 miles, and we're looking for the hypotenuse, right? So we usually label these A, B, and C, although here I called it D for distance. So we need the Pythagorean theorem here. And this we talked about in previous sections, previous videos quite a lot. So c squared equals a squared plus b squared. Right? And we're looking for c. Right? That's the distance. Right? And we know a is 20 and b is 48. So let's plug those in. So this is 20. Don't forget to square it. 20 squared plus 48 squared. And when we add all these up, 20 squared I know is 400. 48 squared, 2304. So this is going to be a total of 2704. But be careful, that's not miles, right? That's square miles. In order to find c, we have to take the square root. So let's do that to both sides. Right? So c is the square root of 2,704. I can just squeeze that in there. And you're welcome to use a calculator for this, because this is a pretty big number here. It turns out to be exactly 52, right? So 52 squared, 52 times 52, turns out to be 2704. So this turns out to be a perfect square, the 2,704. But there's our answer, right? How far apart are they? They're 52 miles apart. So that was the distance, right, after 4 hours. So the answer to the original question, how far apart are the two ships? We can now say definitively they were 52 miles apart. All right, so that's number 4. Not an easy one. Number 5, find the length x of the side of the following triangle. So, right, so if it's a little too small, I think I can draw another one a bit bigger here. All right, so this side is supposed to be 12. They're not giving us units, so 12 units. The hypotenuse is 20, and we're looking for this side x. Okay, so having done the previous problem, hopefully you realize that this is, again, a right triangle, and so we're just going to use the Pythagorean theorem. So a squared plus b squared equals c squared. So here, a, we don't know what a is, so we'll call it x. We know that b is 12, and c is 20. So 12 squared is 144, and 20 squared is 400. So when you subtract the 144 from both sides, I think we get 256. And right, that's not x, that's x squared. So taking the square root of 256, you get 16. So, yep, the length x here has to be 16 units. And that's the answer to the question, right? Right. Now, I didn't tell you whether it's, 16 feet, 16 inches, 16 meters, 16 miles, right? So 16 units, whatever distance, whatever units we're using for distance here. Okay. Something very subtle. You notice when I took the square root of both sides, again, having been through, the whole section here, and in particular in chapter 11, you remember that you should always add a plus or minus. So why isn't it plus or minus 16? Well, let's think about what does it mean to be negative 16 feet or negative 16 miles. How can you have a negative distance, right? Yeah, so here we're going to ignore the negative solution. We can cross it out as being a non-physical distance, a right? So it doesn't make sense for distance to be negative. So yes, absolutely, when you take the square root of both sides, you should always remember that there's a positive square root and a negative square root. Here we're just ignoring the negative square root, and we're just going to make it positive 16. Oh, I'm sorry, I'm putting miles when we don't know what the units are. It could be 16 feet, it could be 16 inches, it could be 16 centimeters, right? So 16 units of distance. All right, so that's number 5. Okay, and in number 6, there's many parts here. I want to say 15 or so. So I'll try to do as many of them as we can here. And the directions just say simplify, right? So we're just going to simplify, write with positive exponents, right? So no negative exponents, and assume all variables are positive. So remember what that means. That's good for us because we don't have to worry about absolute value. Remember I mentioned earlier that if you're taking the nth root of x to the n, that's not necessarily x, right? It's going to be x if n is odd. And it's going to be the absolute value of x if n is even. Oops, sorry. If n is even. But when x is positive, the absolute value of x is just x, if we're assuming that x is positive. So here we don't have to worry about absolute value at all. All right. Yeah, and we're starting very simple here. The square root of 121, boy, I hope you know that one by heart. If not, well, you have a calculator, and your calculator will tell you that it's the number 11, and that's all there is to it, right? For part B, this is the square root of negative 12 squared. So square root means, right, the exponent here is the same as the index. So this is really just negative 12 to the 2 over 2, which is just 1. So the exponent here is just 1. So this is indeed negative 12. So I hope I didn't fool you with this. This is not negative 12, right? And the reason is because of what I just mentioned, what I just erased essentially here, right? That 2 is an even number. So we have to take the absolute value of negative 12, which is positive 12. Okay, so the answer is not negative 12. Right, so I hope I didn't fool you with that. It's positive 12, not negative 12. Another way to see that is just to go through this step by step here, right? Let's look on the inside here, right? Let's take the square root of negative 12 squared. So what we need to do first is negative 12 squared. What's negative 12 times negative 12? Right, so it's a negative times a negative, which is positive 144. What's the square root of 144? 12, right? Not negative 12. So yeah, be very careful here because you see I almost got it wrong myself. I said this was negative 12, and it's not. It's positive 12. So if you put negative 12, yeah, you're going to get it wrong. Part C, the cube root of negative 64. Okay, so it's negative, but it's a cube root, right? So there's nothing funny going on here. This is just going to be negative 4. Okay, and you can check. If I take negative 4 to the power 3, I get, well, negative 4 times negative 4 times negative 4, which is indeed negative 64. All right. Part D, we have this, negative square root of 81. Well, the square root of 81 is itself equal to 9, but there's a negative in front, so we make it negative 9. That's all it is, right? All right, part E, this is going to be, let's see if I can scroll that down here. This is going to be our first non-trivial one. The square root of 25 x to the 8 over 36 y to the 6. Okay. Now, since we're assuming x and y are positive here, we can split all this up. And by now, we can do it all at once, right? We have the square root of 25 times the square root of x to the 8 all over the square root of 36 times the square root of y to the 6. And I can do that because I'm just multiplying and dividing, right? I'm not adding or subtracting here, right? All right, square root of 25, right, is just 5. The square root of x to the 8 is x to the 4, right? The square root of 36 is 6, and the square root of y to the 6 is y to the 3. All right. Yeah. All right, so part F, I think I can squeeze that over here on the right. We have negative square root of negative 9. Tricky one because you might think the negatives cancel, right? After all, if I just take negative negative 9, that would be positive 9. But don't forget there's a square root here. So these negatives absolutely do not cancel each other out. So let's look at what is the square root of negative 9. And then we'll just put a negative sign in front. Okay, so the square root of negative 9 is the square root of 9 times the square root of negative 1. And remember, the square root of 9 is 3. The square root of negative 1 is I. It's imaginary. So we just have negative 3 times I. If you were doing this way back in section, I believe it's 10.1 or 10.2, you would just reply that, look, this is not a real number, right? Because we didn't know what I was back then. But now we do. We know what I is, right? You should know that I is the square root of negative 1. And so the answer here should just be negative 3i. All right, so let's go on to part G. Okay, so for part G, we have the square root of c to the 12. And again, we just want to simplify, right? So one way to think of this is, right, it's the square root of c to the, well, 12 divided by 2 is 6. And then 6 times 2 is 12, right? So when the exponent and the index match, they just cancel each other out. And this is c to the 6. And by the way, even if you forgot, right, that if c is negative, that you would need absolute value, even if c is negative, c to the 6 would still be positive, right, because 6 is even. So, right, so this would be c to the 6, regardless of whether we knew that c was positive or negative. But we're assuming c is positive, so, right, so we definitely don't need the absolute value. But in this case, we didn't need it regardless, right? For part H, we have, let's see, the cube root of 27 times the cube root of a to the 12 times the cube root of b to the 33. Right, so the cube root of 27 is just 3. The cube root of a to the 12, well, right, so one thing I didn't mention in part G is you can also just convert it to an exponent, which is 12 over 3. But 12 divided by 3 is 4, right? So this is just a to the 4. And then the cube root of b to the 33 is b to the 33 divided by 3, which is 11. So there we go, 3a to the 4, b to the 11. Right. So now you should be comfortable with this. So let's split all this up. This is the square root of 16, the square root of x to the 16, divided by the square root of 25, the square root of y to the 10, and the square root of z to the 4. So doing everything all at once here, the square root of 16 is 4 in the numerator. And the square root of x to the 16, yeah, be careful, it's not x to the 4, right? You're dividing by 2. So 16 divided by 2 is 8. So this is x to the 8. And in the denominator, the square root of 25 is 5. The square root of y to the 10, well, 10 divided by 2 is 5. So the exponent of y is 5. And then the square root of z to the 4, this is 4 divided by 2, which is 2. So z to the 2. And oops, that's it for part I. Okay, J, K, and L, these should be very routine at this point, simply because there's no variables here. They're all just numbers. So 16 to the 3/4, remember, is the 4th root of 16 cubed. But instead of doing 16 times 16 times 16, which is a pretty big number, it might be more helpful to do the 4th root of 16 first and then cube it. Right? Because the 4th root of 16 is just 2, and 2 cubed is 8. That's probably the fastest way to get it. Right? Negative 8 to the power negative 4/3. All right, so first of all, what does it mean when the exponent is negative? It doesn't mean it's going to cancel this negative. Not at all. It just means you take the reciprocal. So this is 1 over negative 8 to the positive 4/3. Sorry for writing the fraction this way, but otherwise it's going to be a little bit smaller. So 1 over what? So we have the cube root of negative 8, and then all that raised to the power 4. So let's see, the cube root of negative 8 is just negative 2, and then negative 2 to the 4th power, well, negative 2 times negative 2 times negative 2 times negative 2, so that's going to be positive 16. So we just get 1 over 16. And finally, negative 27 to the 2/3, so this is going to be the cube root of negative 27 to the power 2. So the cube root of negative 27 is negative 3, and negative 3 squared is positive 9. So yes, be careful with K and L. There's a lot of negative signs here, but right in it, the answer ends up being positive. And the main reason for that is because the numerators here are even numbers, and when you have an even number of negative signs, right, they cancel and become positive, right? A negative times a negative, right, is going to be positive. Okay, all right, so moving on. Okay, last three, m, n, and o. So m is a to the 8 over b to the 12, and then that whole thing to the power negative 1/4. All right, well, when you have a negative sign in the exponent, it just means you take the reciprocal, right? So if you want it to become a positive sign, let's just flip it over. B to the 12 over a to the 8, and then raised to the positive 1/4. Well, right, when you have a fraction, you're dividing. So when you're dividing, you can split it up. This is b to the 12 to the 1/4, all over a to the 8, also to the 1/4. And then by the rules of exponents, all right, this will be b to the 12 divided by 4 divided by 8. A to the power 8 divided by 4. So 12 over 4 is 3, so b to the 3. 8 over 4 is 2, so a to the 2. Right. So b cubed over a squared. So that's part m. All right, part n, we have m to the 2/3 times m to the 5/2 over m to the 7/6, 7 over 6. Okay, so again, there's no reason to convert these to radicals. Just use the usual rules of exponents. Even though the exponents are fractions, all the same rules of exponents apply here, right? So we could do this many different ways. I'm going to leave the denominator alone. And what does it mean when you multiply two exponential expressions? It means you add the exponents, right? So this is going to be m to the power 2 over 3 plus 5 over 2. All right, so how do you add fractions? You need a common denominator, which in this case is just 3 times 2 is 6. So for the first fraction, we'll multiply by 2 over 2, and for the second fraction, we'll multiply by 3 over 3. Right. Why do we do that? So we get a common denominator. This is 4 over 6 plus 15 over 6. And now that we have a common denominator, we just add the numerators. 4 plus 15 is 19. So the numerator is going to be m to the power 19 over 6. Right. All right, now we're not done. We still have to divide by m to the 7 over 6. But if you remember the rules of exponents, here we just subtract. So this is m to the power 19 over 6 minus 7 over 6. And because we already have a common denominator, we just subtract the numerators, right? The exponent will be 19 minus 7 over 6. 19 minus 7 is 12, and 12 divided by 6 is 2. So that's the exponent, right? So this is m to the power 2, or just m squared. All right, and finally part O, we have a to the negative 4 over 9 all over 4a to the 1/3. Okay, so there's not much going on here. It's just the same rule of exponents. We're just going to subtract these two exponents here, right? The 4 in the denominator can just stay there, right? So this will be, 1 over 4 times a to the negative 4 over 9 minus 1 over 3. And again, we need a common denominator, which will be 9. So we'll multiply by 3 over 3, the second fraction. So we're going to get a to the power negative 4 over 9 minus 3 over 9. And I think that becomes a to the negative 7 over 9. Okay. But hang on, we're not allowed to have negative exponents. That was in the directions way, way back. The directions said no negative exponents. All exponents have to be positive. So what does it mean when you see a negative exponent? It means it goes to the denominator. So this will be 1 over 4 times a to the 7 over 9. And yeah, you can write it like this. After all, they're written that way in the questions. But as I think I warned you about, I much prefer the fractions to be written this way rather than this way. But in terms of exponents, since the numbers are so small, you can write them this way. All right, so that's rules of exponents, and in some cases knowing that they're radicals, but in this case it's just questioning, the questions have to do with the properties of exponents. Okay, moving on to number 7, we're still simplifying, and we're still writing with positive exponents, and we're still assuming all variables are positive. The difference here is that these are mostly written in radical form, and so the idea is not to convert to exponents, but to simplify as radicals. Okay, so for part A, what would we do here? We have the square root of 448. Right, now 448 is a big number, and you can check on your calculator. It's not a perfect square, right? So I'm not looking for a decimal, right? It doesn't say to approximate or estimate, right? In that case, you would write the decimal approximation, right, which is about 21.166. Right, but that's not what we're looking for here. We want to simplify, not to approximate. We want the exact answer, just simplified. Okay, so the way to do that is to break this apart into smaller and smaller numbers, right? In other words, just do the usual factor tree, right? So if I divide by, well, I want to divide by perfect squares. So I could divide by 2, but 2 is not a perfect square. 4 is. So if I divide by 4, the other factor is 112. So 4 times 112 is 448. And if I divide by 4 again, 112 divided by 4 is 28. And 28 divided by 4 is 7. Now this is the end of the line because 7 is prime. Right? We can't divide that any further, and in fact it doesn't have any factors that are perfect squares. Right? So, but this is 4 times 4 times 4 times 7. So we could just do the square root of 4 times the square root of 4 times the square root of 4 times the square root of 7, and just break it apart that way. Right. Now the square root of 4 is 2, so this is 2 times 2 times 2 times the square root of 7. And 2 times 2 times 2 is 8, so this is just 8 square root of 7. Okay. Now, in retrospect, what we probably should have done, the factor tree should have been, oops, sorry, that's 448. Right, we should have just done 64 times 7, right, because the square root of 64 is 8, and we would have got the answer much faster. But I don't know about you, I didn't know that 448 was divisible by 64. So I tend to start with the smaller numbers like 4 or 9 or 16 or 25 rather than jump to 64 or 128 or things like that. Okay, part B, the square root of 60, a to the 7, b to the 5. Right, so now we have some variables here, but it works the same way. We can split this up, the square root of 60 times the square root of a to the 7 times the square root of b to the 5. All right, so 60, you should know, is 4 times 15, and 15 does not contain a perfect square. So the square root of 60 we can break apart as the square root of 4 times the square root of 15, but the square root of 4 is 2, so 2 times the square root of 15. Right. Now, what about the square root of a to the 7? So the square root of a to the 7, well, you can think of 7 as 6 plus 1. So this is a to the 6 times a to the 1. So we have the square root of a to the 6 times the square root of a to the 1. And I'm not going to put a 1 there. It's understood. The square root of a to the 6, right? 6 divided by 2 is 3. So this is a to the 3 times the square root of a. And you could do the same thing with the square root of b to the 5. It's going to be the square root of b to the 4 times the square root of b to the 1, right? Because 4 plus 1 is 5. So I don't need the 1 there. And the square root of b to the 4 is just b to the power 2 times the square root of b. So let's put everything that doesn't have a square root in front. So 2, a to the 3, b to the 2. And then everything without a square root at the end, and in fact we can just combine everything, 15ab. Okay, so that's how part B works. Part C, we have a cube root. Okay, so part C, we have the cube root of x to the 4, y to the 11, z to the 24. So let's just break it apart. Cube root of x to the 4, cube root of y to the 11, times the cube root of z to the 24. All right, so right now we're looking for powers of 3 instead of powers of 2 because it's a cube root, right? So we can break this apart as the cube root of x to the 3 times the cube root of x to the 1, right? Because the cube root of x to the 3 is just x. So we have x times the cube root of x. Right? You can see how this does us no good to split it up as the cube root of x squared times the cube root of x squared because, right, 2 is not divisible by 3. All right, so you would do that if you have a square root, not a cube root. Right, same thing with y to the 11, right? We want y cubed, and in fact we can do 3 of them, so y to the 9, and 11 minus 9 is 2, so there's 2 left over, right? So effectively what I did here is I just divided 11 by 3, and you get 3, with a remainder of 2, right? So where's this 3? It's technically y to the 3 times 3 is 9, right? And you can see where the remainder goes. The remainder is separate here. Okay, so yeah, the cube root of y to the 9 is just going to be y cubed. That's this 3 here, right? And then times the cube root of y squared. And again, that too comes from the remainder. All right, and finally, the cube root of z to the 24. So 24 divided by 3. Well, this works out nicely because it's 8 with no remainder. So this is just going to be z to the 8. Yep, because it's just 24 divided by 3. Right. The remainder, if there was a remainder, that would go under the cube root. If the remainder was 1, it would be z to the 1. If the remainder was 2, it would be z to the 2, and so on. All right, so just put everything in front. X, y cubed, z to the 8, and then we have the cube root of x times y squared. So that's part C. Part D. We have the fourth root of 80x to the 9, y to the 7. I don't think you're going to see the fourth root that much on a test. You'll see square roots a lot, and you'll see cube roots somewhat often. Once you get, fourth roots or fifth roots, I don't think you're going to see that very much. But it's done the same way, right? The fourth root of 80 times the fourth root of x to the 9 times the fourth root of y to the 7. But now we're looking for powers of 4, right? So instead of dividing by 4 or even 8, we should divide by 16. Right? Remember, 16 is just 2 to the 4. So 80 divided by 16 is 5, I believe. So we just get the fourth root of 16 times the fourth root of 5. And the fourth root of 16 is exactly 2, so 2 times the fourth root of 5. For the fourth root of x to the 9, we can do the fourth root of x to the 8 times the fourth root of x to the 1, right? Because 9 is 8 plus 1. Yep, so the fourth root of x to the 8 is just x squared times the fourth root of x. And then finally, the fourth root of y to the 7 is the fourth root of y to the 4 times the fourth root of y to the 3, right? Because 4 plus 3 is 7. The fourth root of y to the 4th is just y to the 1, and we'll leave the fourth root of y cubed. So we have a 2 in front, an x squared in front, and a y in front, and then the fourth root of 5xy cubed. And let me warn you one more time. I know I did this earlier, that if you're sloppy, you could get this wrong, right? So if you write 2x squared y, fourth root of 5xy cubed, it's a little sloppier, and you might think that's no big deal. It looks fine to me, but it doesn't look fine. It doesn't look like it's the same thing. Right? And you should tell me, you should notice where is this different here. So I would claim this looks to me like a lot like y to the 4th, right? This is y to the 1, not y to the 4, right? So this looks like y to the 4th times the square root of 5xy cubed. But it's not a square root, it's a fourth root. Okay, so right, the sloppiness is that the 4 looks a lot closer to the y than it does over here. Okay, so yeah, I would mark this wrong because of that. So yeah, don't make that mistake, right? The 4 should go much closer to the radical than it does to the y. All right, so as long as you don't make that mistake, you'll be okay. Let's do part E. All right, so part E is the square root of 50 plus the square root of 8. Right, so here we're adding two radicals, And I hope you don't make the mistake of saying that this is the square root of 58. If you do that, you will definitely get it wrong because it's not the square root of 58. And you can check that on your calculators. It doesn't work out that way, right? So it's very similar to fractions, right? Remember, in fractions, you need a common denominator. Here, right, you need a common root, right? You have to have a like radical instead of like denominators here. So 50, we can break that apart as, well, 25 times 2, right? And so this is just going to be the square root of 25 times the square root of 2. With 8, we can do 4 times 2. So we have the square root of 4 times the square root of 2. And the square root of 25, 25 is a perfect square, so the square root of 25 is 5. So 5 times the square root of 2. And the square root of 4 is just 2. So we have 5 square root of 2 plus 2 square root of 2. And you should recognize that that's just 7 square root of 2. Right? No different than if I have, 5x plus 2x. You should immediately recognize that as 7x. Right? So the x here is just this square root of 2. All right? So yeah, your answer should be 7 square root of 2. Right? Because I'm not looking for a decimal here. Right? We're simplifying, not approximating. Okay, part F, we have the square root of 75x to the 5 minus x times the square root of 12x cubed. Okay, again, subtracting a lot like adding, well, except it's subtracting, of course, but it's done the same way, right? So 75, I mean, we could do this a number of ways. You can do 5 times 15, but I don't see any perfect squares there. So you'd have to keep going. 15 is 5 times 3, and when you write this as 5 times 5 times 3, oh, you see the perfect squares, right? 25. Right. So what we should have done is just 25 times 3. So we're going to get the square root of 25 times the square root of 3 times the square root of x to the 5th, but to get a perfect square, we'll write it as x to the 4th times x to the 1. And then minus, well, let's come back to the second term, right? Let's finish this. The square root of 25 is 5. The square root of 3 is the square root of 3. The square root of x to the 4th is just x squared, and the square root of x is the square root of x. So we have 5x squared times the square root of 3x minus what? Okay, so we're going to have x times the square root of 12 times the square root of x cubed. The 12, of course, is just 2 times 6, but those aren't perfect squares. Probably better to do 4 times 3, right? So we have minus x square root of 4 square root of 3, and then the square root of x cubed is the square root of x squared times the square root of x to the 1, right? So what we're going to end up here, I'm going to need another line. We have x times 2 times the square root of 3 times another x times the square root of x. So all of this becomes, let's see, 2x times x, right, is x squared times the square root of 3x. Okay, so putting this all together up here, we're going to get 5x squared times the square root of 3x minus 2x squared times the, square root of 3x. And you can see you're just subtracting two like terms here, x squared, square root of 3x. Right, so we have 5 of those minus 2 of those, which means we're going to get 3 of them. So 3x squared, square root of 3x. All right, moving on. Okay, I'm skipping G and going right to H. G, I think, is very similar to F. So if you can do F, you should be able to do G in much the same way. But H, I think, is a little bit trickier because there's a cube root, and then there's also 3 terms here. Right, so let's start with the first one. Right, we have the first term here. We have an 8x in front, so there's nothing we can do with that right now. we have the cube root of 2, the cube root of x, and the cube root of y squared. You can split them apart, but notice that there's no perfect cubes in 2, there's no perfect cubes in x, and there's no perfect cubes in y squared. Right? None of the exponents underneath a radical is bigger than 2. Right? There's no 3's. No. If you have the cube root of x cubed, of course that's just x. Right? If you have the cube root of, let's say, 4 cubed, that would just be 4. Right? But we don't have any of that here. So in the end, there's really nothing to do here with the first term. We'll just leave it as 8x times the cube root of 2x y squared. Okay, it's the second term that we have to play around with, right? So plus what? Well, 54, I'll do this way down here, 54 is going to be what? It's 2 times 27. And you should recognize 27 as a perfect cube, right? The cube root of 27 is just 3. So this is going to be the cube root of 27 times the cube root of 2, right? That's this 2 here. And then the cube root of x to the 4th, you can write as the cube root of x to the 3 times the cube root of x to the 1. And then the cube root of y squared, we can leave that alone, right? So this is going to be 3 times the cube root of 2 times the, cube root of x cubed is just x. And then the cube root of x, cube root of y squared. So putting this all together here, we're going to get 3x cube root of 2xy squared. Right, and I'll leave the first term as it is. Right. And then the last term here, we have x cube root of 16, cube root of x, cube root of y squared. So what do we do with the 16? Well, I hope you're not thinking 4 times 4, right? That would be the square root of 16, would be 4. This is a cube root. So how about 8 times 2? Right? Because the cube root of 8 is just 2. So we split this up as x times the cube root of 8 times the cube root of 2, cube root of x, cube root of y squared. So you can see it was not necessary to split all this up here. You're just going to have, let's see, the x in front times 2 times cube root of 2xy squared. So x times 2 is 2 times x, cube root of 2xy squared. And so when you look at all 3 of these terms here, you'll notice some similarities. This is not the answer, I'm just highlighting it. You'll notice that, right, this is x times the cube root of 2xy squared. This is x times the cube root of 2xy squared. And this is x times the cube root of 2xy squared. All these are identical. Right? So you have 8 plus 3 minus 2 of those. Right? So 8 plus 3 is 11. 11 minus 2 is 9. So 9x times the cube root, let me make that a little bit better, times the cube root of 2xy squared. Right. So, yeah, a little trickier. It turns out that the first one was already simplified as far as everything goes there. It's the second term and the third term that we had to simplify just a little bit. So I hope that helps. Right, letter I, we have the square root of 30 times the square root of 15. Right, so there's an easy way to do this and then there's a hard way. The easy way is to split up the square root of 30, right? We know 30 is 2 times 15. But notice we have this square root of 15 as well here, right? So, yeah, so this square root of 30 is just these 2 terms here. Oops, sorry. So we have the square root of 2 times the square root of 15 times 15. Well, that's just 15 squared, or 225. But the point is the square root of 225 is just 15. So just put the 15 in front of the square root of 2. So that's the fastest way to get it. You can also just multiply 30 times 15, right? Which I believe is 450. And then just simplify the square root of 450. But to do that, you have to make a much bigger tree here. You could do, I don't know, 10 times 45. 10 is 2 times 5, so we're done there. 45 is 9 times 5, and 9 is 3 times 3. So what you're going to end up with is the square root of 2 times 3 times 3 times 5 times 5. Or better yet, the square root of 2 times the square root of 9 times the square root of 5, which is the square root of 2 times 3 times 5. And then 3 times 5 is 15. So you'll still have the square root of 15 times 2, 15 times the square root of 2, right? Same answer. But you'll see it's a lot more work if you get a bigger number. If you multiply the 30 times 15, I think you're making it a little bit harder on yourself. But it can be done that way as well. All right, and I'll do part J, even though it's very similar. It's a little bit harder because of the cube roots. So we have the cube root of 24 times the cube root of 375. And hopefully you learned your lesson here. We're not going to multiply 25 times 375. You get a very big number. You know, and your calculator can do it very easily, but your calculator, I don't think, is going to help you simplify this, right? Well, okay, maybe it will, but that's not how I want you to think of this, right? I want you to think of simplifying the smaller numbers, right? So 24 is just, well, 8 times 3. So it's the cube root of 8 times the cube root of 3. Right. What about 375? So 375 is certainly divisible by 5. I think it's divisible by 25. So 375 divided by 25, my calculator says 15. Yeah, so I'm sorry, 25 times 15. There we go. And then 25 is 5 times 5. 15 is 5 times 3. So we see our perfect cube here is, right, 5 to the 3, or 125. Right. So we get the cube root of 125 times the cube root of 3. Right, so cube root of 8 is 2. Cube root of 3 is just the cube root of 3. Cube root of 125 is just 5, and then the cube root of 3 is again the cube root of 3. Okay, so we can multiply 2 times 5, and then times the cube root of 3, well, times the cube root of 3, cube root of 3 squared, right? So 2 times 5 is 10, and then the cube root of 3 times 3 is 9. So 10 cube root of 9, right? Yes, you would have got the same answer if you did 24 times 375, which is the cube root of 9,000. And if you did it that way, you might have thought, well, let's just take the cube root of 9 times the cube root of 1,000. And because the cube root of 1,000 is just 10. Right. And just put the 10 in front. Right. So same answer. And maybe that was a little bit easier if you noticed that 9,000 is 9 times 1,000, and then the 1,000 being a perfect cube. The point is you get the same answer either way here. All right. And taking a cue from the last one, I think even though these are square roots, I think we could just multiply everything here. Right. So 3 times 21 times a squared times a to the 5th times b squared times b. So this is just the square root of 63 a to the 7, b to the 3. I hope you weren't thinking a to the 10, right? You're not multiplying the 2 times 5, you're adding 2 plus 5 here, right? Right. And now it looks very similar to a previous one. If you split this up, you get square root of 63, square root of a to the 7, square root of b to the 3. And 63 you can split up as 9 times 7. And then square root of a to the 7, you have square root of a to the 6 times the square root of a to the 1. And the square root of b cubed is the square root of b squared times the square root of b. So square root of 9 is 3, square root of 7 is itself. Square root of a to the 6, right, is a to the 6 divided by 2, so a to the 3. And then square root of a. Square root of b squared is just b times the square root of b. Remember, we're assuming b is positive, so we don't need absolute value. All right, so 3a cubed b, and then finally the square root of 7ab. So I think that's it. So I think in this case, instead of splitting everything up into smaller and smaller pieces here, it made sense to combine everything and then split them up. But either way you do it, you should get the same answer here. All right, so 3a cubed b times the square root of 7ab. L, I think you can handle L. Should be pretty easy. I would just distribute, right? Because the square root of 2 plus the square root of 6, I don't think there's going to be a very easy way to combine those, right? It's not the square root of 8. You know that already. And they're just not like radicals. So why don't we just distribute the square root of 18? We have square root of 18 times the square root of 2 plus the square root of 18 times the square root of 6. Right. So that's the square root of 18 times 2. 18 times 2, I believe, is 36. And then 18 times 6, 108. And of course, these don't look like radicals, but the square root of 36 should be very familiar. It's just 6. And the 108, what's a good way to split that up? Well, it turns out to be 36 times 3. So this is going to be the square root of 36 times the square root of 3. And again, square root of 36 is 6. So 6 plus 6 square root of 3. Right? Actually, I would also factor out a 6 here. I mean, you don't have to. I would really accept either, but I think 6 times 1 plus the square root of 3 maybe looks a little better. Right. The one thing you have to be careful of, because this is a common mistake, is people write this as 12 square root of 3 because it looks like you're adding 6 plus 6. And you just cannot do that. Right? You know, these are not like terms. Right? Think about 6 plus 6x. Right? That's not 12x, it's just 6x plus 6. Right? You can factor out the 6, but you're not adding 6 plus 6. Right? It's 6 plus 6x. Two different things, unlike terms. Right? If you had 6x plus 6x, well, then you would have 12x, right? Like terms. Those you can add. Okay, so just make sure you don't fall into that trap here. It's not 12 square root of 3. It's 6 plus 6 square root of 3, or 6 times 1 plus square root of 3, if you factor out the 6. Okay, part M, square root of, square root of a, I forgot the square root, minus 3 square root of b, times the square root of a plus 3 square root of b. Okay, so this you should recognize as FOIL here, right? We have square root of a times the square root of a, square root of a squared. And then the outside terms, we're going to get, let's see, I'll put the 3 in front, square root of a, square root of b, or just the square root of ab. Right? And then the inside terms, you just have minus 3 square root of ab. And then the last, you have negative 3 times positive 3 is negative 9 times the square root of b squared. Oh, well, yeah. Just to make it look similar, right? 3 times 3, right, so 3 squared times square root of b squared. All right, so square root of a squared is just a, right? Because the index is also 2. That cancels the exponent. These two terms add up to 0, right? 3 minus 3 is 0. right? So, 3y minus 3y is also 0. So whatever the square root of ab is, you're just subtracting 3 square root of ab minus 3 square root of ab. That's also 0. So this just adds up to 0. Right. And then minus, I already had 9. 3 squared, 3 times 3 is 9. And then square root of b squared is just b. So this is a minus 9b. I was almost going to skip n because it's very similar. It's also FOIL here. But we'll do it quickly, right? So 4 times 4 is 16. And then 4 times negative 5 square root of y is negative 20 square root of y. The inside is negative 3 times 4 is negative 12 times square root of y. And then the last negative 3 times negative 5 is positive 15 square root of y times the square root of y, which is just y. So you're going to get 16. And then these two terms, they don't cancel, they combine though, right? Negative 20 square root of y minus 12 square root of y is negative 32 square root of y plus 15 times, well, the square root of y squared is just y, so 15 times y. So that's fine. Although you should put the square root at the end, right? So I guess we could write this as 15y plus 16 minus 32 square root of y. As long as you're clear that the square root doesn't go all the way over the 15y. Here you could write it either way, but this way usually looks nicer. Okay, part O, even though it doesn't specifically have the directions rationalize the denominator, the directions are just simplify. But in this case, that's what this means, right? So as a hint, you have to rationalize the denominator here. Okay, and so remember how this works. There's a couple ways of doing this. You could just do a brute force, say, well, I want to get rid of the square root of 12 in the denominator, so I'll multiply numerator and denominator by the square root of 12. And you could do that. The numerator is just 3 square root of 12 times, well, I mean, the square root of 144, which is just 12. Okay, sorry, 12. There we go. Okay, there's nothing wrong with that, but that's not the final answer because, again, the directions said to simplify, and this is not completely simplified. Right. For one thing, right, this is 3 over 12. 3 over 12 reduces to 1 over 4, right? And you still have the square root of 12 in the numerator. So this is the square root of 12 over 4. Right? So all I did was reduce 3 over 12 to its lowest terms, 1 over 4. But there's something else wrong with this. The square root of 12 is also not simplified, right? Because 12 is 4 times 3. So this is the square root of 4 times the square root of 3. And the square root of 4 is 2. So the numerator is really just 2 square root of 3. But now you can see 2 over 4 also reduces to 1 over 2. So this is just the square root of 3 over 2. Okay, so that's one way to get the answer. It's a very long way, to go about it. Because at any stage, right, if you just leave it like this, for example, it's not simplified, right? So you're not going to get it right. And even if you just do this, right, now it has a rational denominator, but the numerator is still not quite simplified. So you have to go all the way here. So another way to have gone about this that might be a little bit quicker, so here's the original problem, 3 over the square root of 12, is to recognize, oh, hey, I can simplify the square root of 12, right? It's just the square root of 4 times the square root of 3. And the square root of 4 is 2, so this is just 2 times the square root of 3. Right? And now we can notice that the problem is the denominator has the square root of 3 in it. So if I just multiply top and bottom by square root of 3, I get 3 square root of 3 in the numerator and 2 times the square root of 9 in the denominator. But the denominator, right, the square root of 9 is exactly 3. Oops. Okay. And now because we're multiplying, the 3's cancel. 3 divided by 3 is 1. And we're left with the square root of 3 over 2. Right? Same answer. I think you would agree this way was a little bit faster. Right, so that's part O, rationalizing the denominator. Oops. Okay, cube root of 5 over 16. And you probably haven't seen too many of these, right? The first thing you might try is the cube root of 5 over the cube root of 16. Right? And taking a cue from the last problem, 16 is not a perfect cube, but 8 is. Oops. So let's do cube root of 8 times the cube root of 2, because the cube root of 8 is just 2. Okay. On the other hand, we can't have, oh, sorry. This is a cube root of 2, not a cube root of 3 here. So yeah, the issue is you're not allowed to have a cube root in the denominator, but I can multiply numerator and denominator by the cube root of 2. Unfortunately, that's not enough because you'll get the cube root of 4. 4 is also not a perfect cube. So you can either just multiply by another cube root of 2, or in retrospect, we should have just done cube root of 4. Right? So 2 times 4 is 8. That will get rid of the cube root. So cube root of 5 on top, 2 cube root of 2 times 4 is cube root of 8. And then we have the cube root of 4 in the numerator. So yeah, cube root of 8 is just 2, and 2 times 2 is 4. Well, here, let's work it out, right? So yeah, 2 times 2 is 4, that's the denominator. And then the numerator is the cube root of 5 times 4. 5 times 4 is 20. So in the end, this is just the cube root of 20 over 4. Okay. And part Q, I really wouldn't bother with this, but oh, let's do it anyway. So we have a over the 4th root of a cubed. So the way to get rid of the 4th root of a cubed is to make it the 4th root of a to the 4. So how do I go from 3 to 4? I just add 1, right? So I'm going to multiply numerator and denominator by the 4th root of a. And what that gives me in the numerator is a times the 4th root of a. And in the denominator, it's the 4th root of, right, a to the 3 plus 1. 3 plus 1 is 4. And the 4th root of a to the 4 is just a. But there you go. A divided by a is 1. So the a's cancel, leaving us with just the 4th root of a. Right. Over 1, right, so yeah, you could write this as the 4th root of a over 1, but when you divide by 1, you don't, right, it's just like multiplying by 1. It doesn't do anything. Okay. So part R is also rationalizing the denominator. You're not allowed to have the square root of 6, right, in the denominator. Right. Numerator is fine. But in this case, right, and we went through this over and over again in one of the previous videos, the trick is not to multiply by square root of 6. That's not going to work, right? And it's not to multiply by the same denominator, 5 square root of 6. That doesn't work either. Right? What you have to multiply by is the conjugate, 5 plus the square root of 6. So the numerator is just 5 plus the square root of 6. The denominator, if we FOIL this, we get 5 times 5 is 25, plus 5 times square root of 6. And then the inside terms is minus 5 square root of 6. And then the last two terms, a negative times a positive is negative. Square root of 6 times 6 is 36. So we can leave the numerator alone. It's just 5 plus the square root of 6. The denominator we can simplify quite a bit. These two terms add up to 0, right? It's like 7 minus 7. It's 0. 5 square root of 6 minus 5 square root of 6 is just equal to 0. Right? All right, so 25 minus the square root of 36 is just 6. And 25 minus 6 is 19. So there we go, right? So 1 over 5 minus the square root of 6 is 5 plus the square root of 6 divided by 19. You can check on your calculator. These are the same numbers, right? Why do we prefer this version? Because there is no square root in the denominator, right? Remember, that's not allowed, right? So there you go. That's part R. We've rationalized the denominator. Okay, part S, 4 plus square root of 5 over 3 plus square root of 5. Right? So very similar to the previous problem. We know, well, first of all, I hope you don't make the mistake of canceling the square root of 5s. This is not 4 over 3. Please don't do that, right? You can only cancel factors. You can cancel things you're multiplying, not adding or subtracting, right? So, for example, if I had 4 square root of 5 over 3 square root of 5, yeah, you're multiplying. So square root of 5 divided by square root of 5 is 1. That would be 4 over 3. But you see the difference here. You're not multiplying 4 times the square root of 5. You're adding 4 plus the square root of 5. So yeah, don't make the mistake of canceling those. All right, so what do? Same thing we did in the previous. We take the denominator, 3 plus the square root of 5, and we switch it to the conjugate, 3 minus the square root of 5. So we're going to multiply top and bottom by 3 minus the square root of 5. Okay, so let's start on the top. 4 times 3 is 12, minus 4 square root of 5, plus 3 square root of 5, and then minus the square root of 5 times 5, 25. So again, I just did FOIL, usual thing, and do the same thing in the denominator. 3 times 3 is 9, and then 3 times negative square root of 5, so negative 3 square root of 5, plus 3 square root of 5. Right? And you can see that was by design. That's going to be 0. We'll do that on the next step. Plus, a positive times a negative is negative square root of 25, right? Of course, we know the square root of 25 is just 5. So what are we doing on this step here? So we have the 12. Negative 4 square root of 5 plus 3 square root of 5 is negative 1 square root of 5. I don't need the 1, so just minus square root of 5. And then the square root of 25 is 5, right? In the denominator, we have 9. This adds up to 0, and then minus the 5. So what do we get? 12 minus 5 is 7, and 9 minus 5 is 4. So we're going to get 7 minus the square root of 5 over 4. And that's our answer for this problem. Again, you're not allowed to have a square root in the denominator. By multiplying by the conjugate, 3 minus the square root of 5, we got rid of all the square roots in the denominator. So this is considered simplified, right? This is not. Even though it's the same number, right? It's not considered simplified. Right? And part T is done exactly the same way, right? We have 2x plus the square root of y in the numerator, and we have x minus the square root of y in the denominator. So we need to multiply numerator and denominator, not by the denominator, x minus the square root of y, but the conjugate, x plus the square root of y. Right, so here we change the minus to a plus. Right, I think in the previous problem we changed the plus to a minus, right, this one here. But yeah, the conjugate, right, change one of the signs. So if we multiply out the numerator, we get 2x times x, 2x squared, plus 2x squared of y, plus x times the square root of y, plus the square root of y squared. And in the denominator, we get x times x, x squared, plus x squared of y minus x squared of y minus the square root of y squared. So let's see, 2x squared is fine. These add up, right? You have 2x squared of y plus 1x squared of y is 3x squared of y. And then the square root of y squared is just y. In the denominator, we have x squared, and then x squared of y minus x squared of y is just 0, and then this square root of y squared is just y. So x squared minus y. And that's it. So, yep, even though it doesn't look simpler, 2x squared plus 3x square root of y plus y all over x squared minus y. This is considered simplified because it does not contain a radical in the denominator. The square root of y is not allowed in the denominator. Okay. Okay, number 8, I am skipping that entirely. They're not going to be on a test. Essentially, number 8 is a throwback to, a time many years ago when we did not allow calculators on tests. So yeah, because you can use your calculator, I think number 8, just use your calculator, right? So yeah, for number 8, those are calculator problems, and I think you can handle those. They're just not good test questions. They're basically testing, do you know how to use a calculator? So I hope you do. But number 9, you want to solve equations containing radicals. Okay, so let's start with part A. We have the square root of y minus 4 is equal to 13. So how do we solve for, in this case we're solving for y. Well, I hope you're not adding 4 because the 4 is underneath the square root. Right? So how do we get rid of a square root? Well, you multiply by itself, right? You square it. But if I square the left side, I have to square the right side. So squaring the square root just gets rid of the square root. Now we have y minus 4 on the left. And on the right, we have 13 squared. 13 times 13 is 169. All right, now you add the 4, right? Now we add 4 to both sides, and we get y equals 169 plus 4, 173. So that's all it is for part A. Part B, very similar. We have the square root of 2x minus 9 plus 5 equals 0. So now notice the plus 5 is not underneath the square root, right? The square root does not extend above the plus 5. So I would subtract the 5 from both sides. Right, so by doing that, I've isolated the square root. You notice that in part A, the square root was already on the left side. So that's called isolating the square root. Now we can get rid of the square root by just squaring both sides. Let me do that on the next step, right? So square root of 2x minus 9 equals negative 5. To get rid of the square root, you square it, and you do the same on the right side. So the left side is just 2x minus 9. The right side, negative 5 times negative 5 is positive 25. You can take it from here, right? Just add the 9 to both sides. 25 plus 9 is 34, and divide by 2. Right? So 34 divided by 2, I believe, is 17. Right? So the answer should be 17. All right. One thing I should have emphasized here is that maybe we should check these answers. If we check the 173, you plug that back into the original equation, and you'll see it works. Right? The square root of 169 is equal to 13. But what about 17 here? If I take the, let's see if I can do this down here. If I plug in x equals 17, what do I get? I get the square root of 2 times 17 minus 9 plus 5. Does that equal 0? Well, 2 times 17 is 34. Right? And 34 minus 9 is 25. And the square root of 25 is 5. And 5 plus 5 is 10. But that does not equal 0. So that's wrong. These are all wrong. So 17 apparently is not the answer. Okay, so what is the answer? The answer is that there is no answer. Right? This equation has no solution to it. Okay. So yeah, be careful. Make sure you check your answers, see if they work. If they don't work, then there is no answer here. There's no solution to part B. Okay. And on some level, you might have noticed that right away. Notice that anytime you take the square root of any number, right, the square root of 100 is 10, right? It's not going to be negative, right? The square root of 100 is not negative 10, right? It's positive 10. So the square root of any numbers is automatically going to be positive, right? You can imagine just a positive sign in front of the square root. So right here, this is a positive square root of 2x minus 9. But the right side is negative. How can you have a positive number equaling a negative number? You can't, right? The only way that can happen is if it happens to be 0, right? Positive 0 is the same as negative 0. That's the only way. But negative 5 is not positive 5, right? So automatically, these two things cannot be equal. You cannot have a positive equaling a negative. That alone should have told you, hey, there's no solution here. But I took the long way around. I didn't notice that, and I just went through, solved the equation, and I got what looked like a legitimate answer, right, 17. But when I checked it, I got 10 is equal to 0, and of course 10 is not equal to 0. So that told me, no, it's not correct. And in this case, it's not because I did anything wrong here. I didn't do anything wrong. I just didn't notice that you can't have a positive equaling a negative. So that's the issue, right? Or if you go back to the original equation, you can't have a positive number plus another positive number equaling 0, right? You can have a negative 5 plus 5 equals 0, but this first term here is a positive square root, right? It's not going to be negative. Okay. So yeah, B was a little bit tricky because the answer is no solution. It's not 17. Okay, might as well do part C as well. Number 9, part C. We want to solve the cube root of the cube root of 5 minus 9x equals negative 7. Now, unlike the previous problem where, wait a minute, the right side is negative, the left side appears to be positive, but hang on, remember the cube root of a negative number could be a negative number, right? So it's not the square root. You can have the cube root of, say, negative 64 being negative 4. So even though it looks like there's a plus sign on the left, this whole thing here could be negative, making it a negative number. Okay, so to automatically put no solution here probably will be wrong. Instead, you just do the logical thing here. To get rid of the cube root, you raise to the power not 2, but 3. Right. If you want to get rid of the square root, you would raise to the power 2. All right, so the left side is just 5 minus 9x. The right side is negative 7 times negative 7 times negative 7, which I forgot. It's negative 343. And you can use your calculator for that. Negative 343, right? Okay, and you can solve for x. Just take it from here, right? I would subtract 5 from both sides. So negative 9x is equal to negative 348. And negative 348 divided by 9 is not a nice number, right? So this will be positive 348 over 9. So let's see, can we reduce this to its lowest terms? 348 divided by 3. Oops. Yep, is 116. So this is, 3 times 116 divided by 3 times 3. So we can cancel the 3's. This is just 116 over 3. Right. Or if you like, it's 38 and 2/3. All right, I would accept either. I will not accept 38.666 or even 666666666. You can put as many 6's as you want. It's a good approximation, but it's not the exact answer. Right? This is a repeating decimal. This just goes on forever here. The 6's repeat forever. Right? So some people write that as 38.6 with a bar over the 6 to indicate that it's repeating. Right? I mean, I would have to accept that, but again, I'm not happy with that. I'd prefer you leave it as 116 over 3 or 38 and 2/3, but I think improper fractions, 116 over 3 is just fine. Okay, so and you can check that that is the answer. X is equal to 116 divided by 3. All right, and finally part D. Again, number 9, part D, we want to solve the equation square root of 5x minus 4 equals x minus 2. Right. Again, the square root on the left is isolated. So all we have to do to get rid of the square root here is just the opposite, or I should say the inverse. You're squaring it. The inverse of the square root is just squared. Right? So the left side becomes 5x minus 4. The right side, well, I'll let you think about that for a minute. All right, it's not x squared minus 4. It's not x squared plus 4, right? It's x minus 2 times x minus 2. It's another FOIL. So you're going to get x squared minus 2x minus 2x, negative 4x, and then negative 2 times negative 2 is positive 4. Okay. Yeah, what you end up with is a quadratic equation. And you've been through chapter 11, so you know how to solve these, right? You got to get it in standard form, so I would subtract the 5x from both sides. And let's add 4 to both sides. So the left side is 0. The right side is x squared minus 9x plus 8. So we have to solve x squared minus 9x plus 8 equals 0, right? I'll just put the 0 on the right. Now, this does come from chapter 10. And in chapter 10, you didn't have the quadratic formula, right? We didn't have completing the square. So how do we solve this? Well, you could use the quadratic formula. You could complete the square. But the easiest way here is just to factor it. This is x minus 1 times x minus 8 equals 0. So if x minus 1 is 0, that gives you x equals positive 1. If x minus 8 equals 0, that gets you x equals positive 8. Okay, so those should be the solutions. But let's go back to the original equation here. The square root of, let me write it down, the square root of 5x minus 4 equals x minus 2. So let's check x equals 1. We get the square root of 5 times 1 is 5 minus 4. Is that equal to 1 minus 2? Well, 5 minus 4 is 1, so we get the square root of 1. 1 minus 2 is negative 1. The square root of 1 is 1, but that does not equal negative 1. So as it turns out, x equals 1 is wrong. Doesn't work. But that doesn't mean no solution. We can now check x equals 8. Maybe that works. If it doesn't work, then there is no solution. But we won't know until we check. Sorry. X is 8, right? So 8 minus 2. All right, so 5 times 8 is 40. And 40 minus 4 is 36. So we have the square root of 36 on the left, and 8 minus 2 is 6 on the right. Well, the square root of 36 is just 6. So indeed, 6 does equal 6. This is correct. So we have our answer, x equals 8. Right? It works in the original equation. So, yep. So the solution is x equals 8, but not x equals 1. You have to cross that out because it is not a solution. We checked it, and we found that it doesn't work. Okay, so again, very important that you check your answers for these. Okay, number 10 should be quite routine at this point. So 10a, we want to write as a complex number a plus bi. So we have negative square root of negative 75. Again, the negatives don't cancel here because 1 is under the square root and 1 is outside the square root. So that tells me that when you take the square root of a negative number, it should be an imaginary number. Okay, 75, of course, is just 25 times 3. Okay, so we can simplify this as negative square root of, well, negative 1 times 25 times 3. And we can split this up, square root of negative 1, square root of 25, square root of 3. So square root of negative 1, you should recognize that as the letter I. The square root of 25 is just the number 5, and the square root of 3 is just square root of 3. Right? We cannot simplify that any further. So I'll just switch the I and the 5 around. This is negative 5i square root of 3. So this negative sign did not go anywhere, right? It's still negative, but the negative sign on the inside of the square root became an imaginary number. Okay, so for part B, the square root of 144 minus negative square root of 81. Yeah, I think you can practically do this in your sleep. Square root of 144 is 12. And the square root of negative 81 is the square root of positive 81 times the square root of negative 1. Square root of 81 is 9, and then the square root of negative 1 is I. So this is really just 12 minus 9i. Right? Either way. All right. And finally, part C, which I forgot already. Oh, square root of 24 plus square root of negative 63. Okay, so again, this goes way back to just simplifying square roots here. 24 is 8 times 3. Oh, but those are not perfect squares, right? This is not the cube root here. This is a square root. So why don't we do 6 times 4, right? Square root of 4 times square root of 6. And for 63 we could do, I don't know, 3 times 21. 21 is 3 times 7. Oh, 3 times 3 is 9. So 9 is our perfect square. So let's do square root of 9, square root of 7. Oh, but it's negative, so don't forget the square root of negative 1. Okay, so we're going to get 2 square root of 6 plus 3 square root of 7, and then square root of negative 1 is I. Okay. So that's it. As long as you're careful that you don't put the square root over the I would accept this. But to avoid that ambiguity, that confusion, it is better to put the I in front of the square root. I would accept either as long as you're not sloppy about it, right? Because if I see this, then it's wrong. You're not taking the square root of I. Okay? The I goes outside the square root. So if you're going to write it this way, just make it clear. Okay. And then for number 11, part A, just simplify and write as a complex number. In fact, at this point, this should look very familiar, right? This is something you might get if you're solving a quadratic equation, right? In fact, you might have plus or minus the square root of, say, negative 36. But here it's just a negative, right? So 4 minus, and then the square root of negative 36 is the square root of positive 36 times the square root of negative 1. Right? So that's just to give you the I here. So 4 minus 6i over 12. But we can reduce that, right? Right? We can factor out a 2. Well, all right. So why don't we do it this way? 4 over 12 minus 6i over 12. 4 over 12 is just 1 over 3. And 6 over 12 is 1 over 2. So 1 over 3 minus 1/2 I. 1/3 minus 1/2 I. Or if you insist on getting a common denominator, you could do that too. Here would be 6, right? So this would be 2 minus 3i over 6. Right. I'm not picky about this. Either way is fine. It did say write it as, a plus bi. In this case, a is 1/3 and b is negative 1/2. Right? So at this stage, I would accept either. All right, and as far as 11b goes, it's just a bigger number, but I think you can handle it. I'll do it very quickly. 32 plus the square root of negative 1152 over 8. So yeah, it's the 1152 that might be a little tricky here. So the negative, we know that's going to turn into an I. It's just a matter of simplifying the square root of 1152. All right, 1152. So we're looking for perfect squares. If we divide by 4, oh, I forgot what I got here. So 1152 divided by 4 is 288. But I think that's divisible by 4 as well. If you divide that by 4, you get 72. 72 divided by 4 is 18. And 18 is not divisible by 4. It's divisible by 2, giving you 9. So 9 is a perfect square. 4 times 4 times 4 is a perfect square. 64 times 9. And then times 2, which is left over, right? So the square root of, so square root of 1152, it's the square root of 64 times the square root of 9 times the square root of 2. That's a 9. So 8 times 3 times the square root of 2, 24 square root of 2. So, yep, this is just going to be 32 plus 24i square root of 2 all over 8. But I think we can reduce that, right? If we divide by 4, we get 4 plus 6i square root of 2. Oh, I'm sorry, we could divide by 8. 32 divided by 8 is 4, right? And 24 divided by 8 is 3. So I think that's it. 4 plus 3i square root of 2. I hope, well, yeah, you see how I got that, right? I just split it up. 32 over 8 plus 24 over 8 times I root 2. So the 32 divided by 8 is the 4, the 24 divided by 8 is the 3, and then the I square root of 2. All right, good enough. Okay, 12a, solve for a, right, the letter a, the variable a. We have m equals the square root of 5a over 3b. So how do we solve for a? Well, the first thing I would think about here is I want to get rid of the square root. And it is isolated, right? Now it's on the wrong side. It should be on the left, but it doesn't matter. As long as there's the square root, and nothing else attached to it, right? If there was a plus 3 here, you would have to subtract that 3 first. So yeah, no problem. Just square both sides. Square the right side, square the left side. So we're going to get m squared equals 5a over 3b. And I think you can take it from here, right? All we're going to do now is multiply both sides by 3b, right, over 1. Right? So on the right they cancel. We get 3bm squared is equal to 5a. Now just divide by 5. And that cancels, so a is just 3bm squared over 5. Or if you prefer, 3m squared b over 5. Order doesn't matter. And that solves for a. All right, part B. The equation is g equals 4c times the cube root of 2a squared over b. And we want to solve for little b here, right? So we want to solve for this denominator here, right? But it's also under the cube root, so we could cube both sides. Or notice the 4c is not under the cube root, so I would divide both sides by 4c first. You don't have to cube root, right? But I think it makes sense to cancel the 4c's on the right. So we have g over 4c on the left. It's equal to the cube root of 2a squared over b on the right. Okay, so now we just do the same thing we did, except it's the cube root. To cancel the cube root, you raise to the power 3 on both sides. Okay, oh, running out of space. Let's see if I can squeeze that in here, right? So when you cube the left side, you get g cubed over 4 cubed times c cubed. But 4 cubed, 4 times 4 times 4 is just 64. Right, and on the right, all we did was get rid of the cube root. So you can take it from here. You just multiply by the LCD, or just cross multiply, right? If we multiply b times g cubed, we get, I'll do that over here, b times g cubed. And if we multiply, let's see, 64c cubed by 2a squared, we're going to get 64 times 2, 128, a squared times c cubed. Okay, so by cross multiplying, I got rid of the fractions. Remember, we're solving for b, but we have bg cubed, so divide by g cubed. So that these cancel. So b is just going to be 128 times a squared times c cubed, all divided by g cubed. And that's part B for number 12. And this video is getting quite long, so I think I will end it here. Now this was all chapter 11. Oh, I'm sorry. It was chapter 10. Yeah, all of this was in chapter 10. So in the next video, in the second part, we will do the problems in chapter 11 and 13.